I'm going to get my timer. So not to be rude, but given the nature of this, the timer will go off when your time's up.
Okay.
All right, so we have Walter Bridges. Go.
All right, thanks. I'll just go ahead and say for all the speakers here, it's a real pleasure to be here. Thanks for inviting me, all that good stuff. So yeah, I want to talk about this specific example. So there's been a lot of work on unimodal sequences. These are not as nice as partitions for all sorts of reasons, but recently there's been lots of workarounds to these obstructions, and we can still say some pretty strong things actually. So the rank of a unimodal sequence is defined as the difference between the parts to the right and the left of the peak. So here would be -2. And this two-variable generating function here is what we call a false Jacobi form. And its derivatives give you the generating functions for the moments of this rank statistic. So I think Frank and Atkin introduced moments for cranks and ranks for maybe arithmetic reasons, but as we saw in Michael Griffin's talk, moments are also important because they determine the distribution of a statistic. And so with Katrin-Bringman, we prove precise asymptotic series that I'm not going to write down exactly, but up to polynomial error, we can estimate these things, which is much stronger than what you get without connections to modularity. So there's some modularity of the false data function we're using. So the sort of the naive thing you would do here is to just compute the derivative and plug it into the circle method. And that's what Bringman, Malberg, and Rhodes do in the first paper where they do this for the rank and crank. But if you want a more precise asymptotic series, you can use the Jacobiness, apply the Jacobi transformation, and then pick off Taylor coefficients and plug that into the circle method. And recent work of Bringman and Nazaroglu shows you how to complete a false data function a la Zweigers into a real holomorphic Jacobi form. And so this is the key that we use to work out the transformation for this false data function that we need. And yeah, so this false data function here, its error to modularity can be written in terms of an Eichler integral. And yes, that's basically it. And the last thing I'll say is that, you know, these are very widely applicable techniques. And in Amanda Folsom's talk, we saw a couple of examples of ranks of things that would fit into this machinery. So ranks of overpartitions and strongly unimodal sequences. These are both examples of mock Jacobi forms. So it would be an open problem to do the same for those. That's it. Thanks.
In 5 seconds, so great job. And good results. Any quick questions? All right. Alejandro? And maybe for each talk, the next speaker can creep up right before.
I think this is one.
All right. Well, I'm going to talk about, it's a little tangential to this conference, but I'm going to talk about inversion formulas for the modular J function. It's joint work with a fellow graduate student, Badri Pandey at UVA. Right, so the modular function is very important. It parametrizes isomorphism classes of elliptic curves. It's central to the theory of complex multiplication. And of course, it encodes the representation theory of the monster. One of the first observations is that it's a bijective holomorphic function from the fundamental domain to C, can be extended to the Riemann sphere. So one of the first questions one could ask is there an inverse map to this? So other results have been known in the past, but recent developments have added a twist to this. So let T have a non-trivial stabilizer, namely I, rho, and infinity. This particular work by Calderaro, He, and Wang are focused on I and rho. Consider the Taylor series of J around tau. And the conjecture is that there are special functions. I just put a placeholder name here, omega tau. That's actually not the actual notation. But if you evaluate this Taylor series at at these special functions, you should get a rational function in T. And this is indeed an inversion formula, since it's basically just J evaluated at something, and you get a rational function. So this conjecture was proven quite recently, immediately after. And a key step is to use an identity of this form. So it's J evaluated at some quotient of hypergeometric functions, and you get this rational function. So this is work by Berndt, Bargava, and Garva. So here, if you notice, if you evaluate at gamma equals 0, you get this simple pole on the right-hand side, so infinity. And on the left-hand side, if you compute that, you also get infinity, which is just a generalization, so to speak, of J at infinity is infinity. So the new wrinkle here in this work is that what happens at these other elliptic points? Well, at the elliptic points. So here, just as a refresher, the Gaussian hypergeometric function is defined this way. So it's a Q series. And in order to move the pole at infinity to these other points, we need these uniformizing maps. And so here, right, so you just move, so I goes to 0, rho goes to 0. And we normalize by dividing by the Chala-Selberg period. This simplifies the power series. And our results is you take these hypergeometric functions, these quotients, and you get these rational functions. And as you can see, this specializes. If you evaluate at t equals 0, you get 1728 on the first one and I on the left-hand side. And here you get 0 and rho on the other side. So this is a sort of generalization of that, of those identities. I don't know which one.
Yeah, I remember seeing that in different archives. It's fascinating. It's like this crazy thing.
I know you sent it to him.
I knew him
There.
when I was an undergrad. All right, so we have Benjamin Brindle.
Yeah, so thanks for having me here for these 3 minutes. And yeah, I want to talk about combinatorics and some kind of partitions. Yeah, and we start with the combinatorial theorem. It looks horrible. We don't want to go into the details, but you can prove it when you consider the generating series of both sides, and then you will get Q analogs of multiple zeta values. In particular, Q analogs in the model due to Bradley and Jar. That's on the next slide. Okay, sorry. And what I wanted to say about this identity is that it is some real identity and not only an arrangement of summands. As you can see, for example, here, when you pick some special case and a more special case, when you take n equals 7, then you see that the products of binomial coefficients on the left and on the right side are indeed different ones, but the sum is, of course, the same. Yeah, so the proof is, as mentioned before, by using the generating series, giving you Bradley-Shaw Q multiple zeta values. And now the identity we have seen is only duality in this model, which is a very strong tool in this whole field of Q analogs of multiple zeta values. Indeed, and a little remark or why this is related to the topic of the conference is that Q analogs of multiple zeta values are.
That's not your time.
Oh, sorry.
Okay, good. What did I want to say? That Q analogs of multiple zeta values in some more general sense are deeply connected to modular forms or quasi-modular forms. And yeah, that's the reason why they are interesting. And another reason we have seen yesterday in Anton Müller's talk, there exactly those Bradley-Shah Q multiple zeta values also occurred. And so these are really cool and interesting objects. And last, I want to say that we can also consider our theorem in some more visualized way, namely as partitions where we mark rows and columns in some way of the Young diagram. And the open question is how to construct a bijection of both sides. So we know there has to be a bijection because of the equality in the theorem. But yeah, such a bijection is not known so far. Thank you.
Well, we have another open problem getting into our open problem session. It was a little quick, but it was recorded. So anyone interested in the problem, Frank is interested in the problem. Krishna had to get it right. Any questions? All right. Thank you again.
Nicholas, I think you're next.
Okay, Nicholas, are you ready?
Ready. Thanks awfully. So very quick, thanks obviously to Ian and Larry. Appreciate your work very much. I just wanted to give a very brief footnote to what Professor Ajayi said yesterday. She was talking about Ramanujan's third order Mach-Fade function, which I put here, but didn't make a typo. And she described a partition function, P omega n, which counts the number of partitions within where all the odd parts are less than twice the smallest part. I won't give any examples because no time, but she gave some examples. It's a very respectable function. And it's de facto enumerated by omega q, which you see here. And since you can define P omega, you can define a smallest parts function for it. And I mentioned this in passing yesterday. Ajayi gave some congruences, I think, for linear powers of 5, for just mod 5. There is a congruence family for infinite powers of 5, and this is what it looks like right here, which is kind of a pretty little result. And it's proved as a consequence of another congruence family for this function Cn. I give this very, very quickly. You define Cn as the coefficient of this function here, where E2 is just your normalized holomorphic part of the Eisenstein series. And if you can prove this congruence family for C of n, powers of 5, then the congruence family for SBT omega follows. And because it's my talk, I guess I'll say the little contribution I made to it. It's very, very little. If you define the generating functions in a very natural way, I'm calling them L alpha here. You just want to show that L alpha is divisible by 5 to the alpha. And Wang and Yang did that. This is what their version of it looked like. So F is weakly holomorphic modular form. It's just along for the ride, doesn't cause any trouble. T and rho are eta quotients. And you can see the coefficients are all divisible by 5, which looks really nice. The thing is, this is over gamma 0, 10, and that has genus 0. So why you're using two functions is kind of peculiar. So I studied this and came up with a new proof. Here's my identity for L1, for example. It uses only one function, a Haupt module, and it has this nice rational polynomial structure, which has to do with the complexity of the cusp count. There's more than 2 cusps on a modular curve, and that leads to more interesting identities. And there are similar identities for L2 and L3. X is just an eta quotient. I go over that quickly, and that's the version I gave of the proof, which I'm kind of proud of. But it's just, yeah. And I've used the same techniques through other Mexican congruence families. So I think I'll stop there. Thank you, guys.
Nicholas, you mentioned techniques. I know you've been doing a lot with this localization. Is that the kind of stuff you use?
Yes, exactly that, because it's a rational polynomial, you see, and powers the denominator like that. That's very useful for
And since, of course, you're at risk and you do a lot of computer packages, do you have any computer packages for this localization method or surveys about the method as a whole?
I'm working on a survey myself right now. I don't have an algorithmic technique, although one of the reasons I like this approach is it may open the doorway long-term for an algorithmic approach to congruence families as a whole. That's what makes it appealing. You can pretty quickly, at least the idea is, if you know the associated modular curve, the associated Riemann surface, you can almost immediately select the correct reference functions you need. You can immediately select the right prefactor, that's that 1 + 5x business. You can put it all together really, really quickly. And some of the steps are a little more tedious, but it looks like it lends itself very well to an algorithm framework, which I like.
Great. Well, let's thank Nicholas again.
Give me 1 second. Yeah, I'm right there. All right, let me start. Okay, yeah, so I guess I'd like to start by thanking everyone for coming to the conference. And I guess this is a little bit strange, but in the 2 years since we started planning this, I've moved universities. And so in order to receive funding from my university now, I have to give a talk. And so, yeah, and actually, I noticed on Benjamin's slides, I completely forgot I should officially thank the ERC grant. They're the people funding me. I forgot to put that in my slides, but yeah, so I want to talk a little bit about a work in progress that I think I'm officially is no longer going to be a work in progress soon. And so the motivation, I guess, comes from 2 places for me. One, just beautiful identities. And so, for example, there's this beautiful identity due to Dyson about the modular tau function where you can write it. And this bottom thing, well, if you recognize maybe that lattice, it comes from something to do with the A4 lattice. And then my second motivation for this project is Ramanujan type congruences. And so I dug up just an example this morning, did a little literature search. For example, if you look at over partition pairs, this function was studied by Brinkman and Lovejoy. And my kind of philosophy over the last year or so is that if there's Ramanujan type congruences, there's often a theta function running around. And so you can actually rewrite this like this. And then that implies that you get some congruence modulo 3. And so maybe a natural question is, we like statistics that explain these types of congruences, like the rank and crank. And so how do you lift something like this to maybe a Jacobi form that keeps track of that statistic? And so, for example, I won't maybe explain how, but you can quickly do this. And I claim that this is a crank type function that explains this. And so the way, since I don't have time for details, I'm going to throw a couple things at you, but you can essentially define Jacobi forms associated to some Hecke character. And so you should think of this lattice index on some level as really transforming with respect to the Weil representation, like what Nick Anderson talked about earlier. And in special cases, so here k = 1, you get something more explicit. And so once you have that, I guess I want to go back and say that we have this explicit character here coming from the Hecke character and our quadratic field. And so then you can go searching for identities by matching characters. Maybe I'll skip that one because it's a little easy. But if we look at powers of eta, we can cook up a Hecke character. And then what we get is actually some Jacobi form that simplifies to just the 14th power of eta. And so this is one way you can lift things. And I guess if you allow me to have 15 more seconds, I'll end with an open problem that there is not a known product form for the thing having to do with the 26th power of eta. And so this is why this has been work in progress. And I think I'm officially admitting defeat. So I can't find a product form for this. And if you can, I think you can solve a really nice open question of Dyson.
And Dyson posed it in this missed opportunities paper, and Also, Sayre very heavily highlighted it, so it's a very old question that Dyson and Sayre really like. So
Yeah.
really nice result.
Part of the reason I've been holding on to it with no progress for so long. All right, so I believe the next two people are going to be chalk talks. So just let me adjust the camera. Andreas, are you going to need both boards or just one?
Whatever you can give me.
Oh, sorry.
Oh, sorry. Okay.
Yeah. How about use this board?
Okay.
Yep. All right, ready? We have Andreas.
Hello, everybody. I'm Andreas. I'm a third-year PhD student in the group of Katrin Bringman in Cologne, and I'm very happy to be here. It's actually my second in-person conference at all, so yeah, I enjoy every minute of it. And my very few time I spend on advertising locally harmonic mass forms. That's the stuff I got into from the last 2 years in my research. So what are locally harmonic mass forms? Very briefly, we saw yesterday what harmonic mass forms are in the talk of Amanda. So I try to assume this. And now what I'd like to do is to maybe pay a price and that gain something back. So mass forms, if you recall, are kind of these are always modular objects, as we all know and love. Then the second condition we always need is kind of the harmonicity condition. So for the hyperbolic Laplace operator, and the third condition usually is the growth condition. And harmonic mass forms world is this linear exponential growth at the cusps, for example. And in the locally harmonic mass form world, you have a better condition. You actually allow it just restrict itself to polynomial growth at the cusps. And the price I pay is that I just not get a global behavior, but a local behavior by saying, okay, I want harmonicity outside some small set X in the upper half plane. And then I have a condition with a limiting behavior on the set X. Well, there's a technical paper introducing these objects. So 10 years ago by Katrin Bringman, then Kane and Winfried Cohn. And this is their definition here is motivated by a peculiar first example, which they call the curly F. So this is the integral binary quadratic form world, and this is basically built as follows. So you have some local factor here. This is a sign factor, then the weight factor, so summing over all Q with some fixed discriminant, and then you have some convergence factor, which is an incomplete beta function, which I don't have space to write in there, but it's not that important. So the geometric picture behind this is you have the upper half plane, and then you your exceptional set in this case are the Wagner geodesics. These are half circles in the upper half plane, and you have infinitely many of them, looking like this. And then you get some infinitely many connected components of the upper half plane, and to each you assign either +1 or -1. Starting with the cup at cusp here at I infinity, you'll start with +1 for this connected component, and then each neighboring connected component switches the sign. And what's the advantage of that is, oh, my time is up already. Okay. Okay, so there's lots of interesting geometry behind this and behavior under the differential operators. So sad I can't tell you this, but to me, actually, it's very beautiful. It's kind of a next level mass form world for me. So thank you very much.
Quick question, Andreas.
Yep.
What can you do with these local mass forms?
So the advantage that they have is that you can kind of apply both operators, the ball operator and the xi operator to this, and get a non-trivial image into both, and it's the same. And so you get an interesting splitting of these guys, which is impossible for kind of globally defined harmonic mass forms. And there's a polynomial involved, which tells you the behavior if you jump between two connected components. And this polynomial has interesting connections to L values and theories, actually. So that's why I'm working on them.
Let's see Andreas again. And I believe your paper on this subject will come out very soon.
Yeah, thanks.
As soon as Paul's done racing, our final lightning talk.
Okay, well, the question of what can you do with this is the question that I don't have an answer for, but these are interesting things that Michael and Nick and I played with for a while, and so I think it's neat and wanted to show you. We'll start with the, now we all know, or I hope we've all seen the standard fundamental domain for SL2Z. If you start drawing fundamental domains for other groups, and this actually came out of, I had a master's student and he was doing some explicit computations, getting ready to defend his thesis, and he drew a particular fundamental domain that came down the -1/2 line and had a semicircle and another semicircle for 1/2 and goes up like that. And if any of you recognize this, you might know that this is the fundamental domain that Sage gives you for the group gamma 05. But this is also the fundamental domain, a fundamental domain for the group gamma 04. And they're the same thing. And surprised me a little bit. I hadn't seen that before. Looking a little bit more. Okay, those are supposed to be the same size. Do the same thing. Here's -1/2, here's 1/2, here's 1/3, here's -1/3. You can draw this fundamental domain, and this is a fundamental domain for the group gamma 06, but also for the group gamma 09, and also for the group gamma 011. And it turns out that if you have essentially any set of gamma 0n's that have the same index, there will be a common fundamental domain for all of them. However, it isn't always as pretty as this. In this particular case, when you actually figure things out, you can start gluing this together. This circle can map to either that circle or that circle or that circle. And when you sew it together 3 different ways, you get 3 for 3 different groups. Again, it turns out that for any set of these groups, you can find a common fundamental domain. It won't always be connected. Computational, you can start with the standard fundamental domain, and well, you have 3 sides. If you go off one of those sides, you can do a finite computational process figuring out if you have a common fundamental domain for any set of 2 gamma 0n's that we looked at, and we found connected fundamental domains. For any set of 3 or more, we did not necessarily find connected fundamental domains. If you want to throw in gamma 08, you can find a fundamental domain for all 4 of those, but it's very disconnected and has some triangles way down by the real line. I guess it's the questions perhaps are, when are fundamental domains like this connected, and what else is this useful for besides being very pretty?
Anyone see anything like this before? Have any thoughts on this interesting phenomenon?
On the connectedness, if you start with this, you get connectedness for some pairs of groups. For other groups, you have to start with that fundamental domain instead to get a connected common fundamental domain.
Well, in my master's thesis, I was drawing fundamental domains for my thesis, and I was also looking at Freaka's original where it has all the computation, and I would consistently get different pictures than him, but they were correct. Like I knew they were correct, and I think for me it was kind of a mystery. But I think I'm going to look more into this because that was the question I had.
The other thing that happened here is we spent some time looking at this and thought we had a nice theorem, and then we found out that Rankin wrote down a similar theorem 50 years ago.
Is it just sets of gamma zeros?
Gamma 1's, the same thing happens. Gamma of n's, the same thing would happen if you ever had 2 of them that had the same index, but you never do. There's a group theoretic property where if the groups, essentially if AB equals BA for subgroups A and B, then it's going to have, you can find a common fundamental domain.
Great. So let's thank Paul again. I think that was a lot of fun. it's a lot of fun and satisfies some grant requirements. We did this for Don Zagi's birthday conference